Welcome back to the Ethereum Fundamentals course. This video is brought to you by Forge College. In our last lesson, we learned how to read and decode bytecode. Now we are going to plug that code in and watch it execute. Think about how a computer gets things done. There's no magic hidden inside the processor. It's entirely mechanical, carrying out tiny tasks step by step. The Ethereum Virtual Machine, or EVM, is built this way. Let's imagine it as a literal, physical machine. It doesn't see the big picture of a smart contract. It reads a continuous ticker tape of single instructions, which we call bytecode. The machine is incredibly fast. The EVM reads this ticker tape millions of times a second. Because it executes these microscopic instructions at such a high frequency, a single misplaced command can ruin a smart contract before the machine can even register an error. To understand, predict, or fix how a smart contract behaves, we have to hit the brakes. We need to slow the machine down and observe the exact state of its environment before and after every single tiny step. Let's lay out the machine's workspace. First, we have the script it reads, the bytecode ticker tape, which is organized as a vertical sequence of opcodes. To read this tape, the machine uses a strict tracking pointer called the program counter, or PC. The program counter dictates exactly which instruction on the tape the machine is allowed to look at right now. Next, the machine needs a place to do its math. We call this the stack. Think of it as a physical workbench, a vertical column where the machine can pile up numbered blocks or remove them as needed. Now we can watch the execution cycle. Step 1 is fetch. The machine looks precisely where the program counter is pointing. Step 2 is decode. It reads the instruction and figures out what specific tool it needs for the job. Step 3 is execute. The machine performs the exact physical action the opcode demands. In this case, push 1 tells it to drop a new value onto the stack. Step 4 is advance. The instruction is complete, so the tracking pointer clicks down to the very next line on the tape, ready to start over. Every Web3 application, even the most advanced ones, runs on this exact fetch, decode, execute, advance cycle, repeating millions of times. But here we had a complication. Real smart contracts are not perfectly straight lines. They require loops, conditions, and branches. How does a machine reading a rigid ticker tape manage to branch out? It uses an opcode called JUMP. When the machine reads a JUMP instruction, it redirects the program counter to a completely different location on the tape. Then there is the conditional jump, or jump if. When the machine hits this, it pauses to check the top block on the stack. If that block gives the machine a green light, meaning the condition is met, it jumps to the new location. Otherwise, it ignores the jump and simply moves straight down to the next line. These jumps are highly sensitive. Jumping into invalid data causes the mechanical gears to instantly jam, failing the transaction and crashing the program. Because jumps create unpredictable, non-linear paths, we cannot simply read the code from top to bottom to guess what will happen. We have to track the machine's exact moves as it runs. To track these unpredictable paths, developers use a tool called an execution trace. Think of it as a meticulous detective's ledger. A trace records exactly where the program counter is, the executing opcode, and a freeze-frame snapshot of the stack before and after every cycle. This ledger makes bugs instantly visible. It proves the exact microstep where the stack lost its alignment. Producing and reading these traces is the core mental model that professional developers and security tools rely on every day to audit the runtime state of high-value smart contracts. Master the 3 golden rules. The execution cycle revolves around the program counter. Stack changes follow fixed rules that never vary, and control flow jumps define the path. Mastering the opcode lifecycle and the execution trace makes the EVM a predictable and manageable tool. In our next lesson, we will put this into practice. We'll use these execution traces to spot common bytecode patterns and dive deeper into how the machine handles memory and storage. This video was created by Forge College. To find more educational resources about the EVM, smart contracts, and Web3 development, visit us at forge.college. See you in the next lesson.